Okay, now we're going to look at components of vectors. And what I mean by that is if you have a vector that goes off at an angle, it could be the result of two vectors working simultaneously. In other words, we're looking at a backwards version of what we looked at before, particularly with the perpendicular vectors. So let's take this scenario here. A plane takes off at a speed of 255 kilometers per hour at an angle of 20 degrees. What is the speed at which it is climbing straight up in the air? And what is the speed at which it is moving forward? So we got two things going on. It's going this way and it's going this way. And the two of them together creates this oblique line or oblique vector. So what we're going to do is we're going to look at those two diagrams from a trigonometric point of view. Since the two components are perpendicular to each other, then this is going to actually be pretty simple compared to some of the works that we did before. So if we look at this right here, this is what we got going on. The plane's taking off this way with a 255 kilometer per hour velocity. And the two components to that is the vertical velocity and the horizontal velocity. And because these two vectors are perpendicular to each other, we create this right triangle. Now, because it's a right triangle, then we can use some basic trigonometry if we identify the various parts. Now, we said it's going up at 20 degrees, so we're going to call that angle theta. Mathematicians really love Greek letters, and they like to use theta for angle measurements, and phi, but mainly theta. This is the hypotenuse, the actual velocity of the plane. It's opposite the right angle here, so that's your hypotenuse. This is your angle here that you're looking at. This is the leg of the triangle. Now the two legs of the triangle are the two components of the right angle. This is the one that's adjacent to the angle. This is the one that's opposite of that 20-degree angle. And if we're trying to find the horizontal component, what we're looking at is, if you can imagine standing, facing the plane in this direction here, and you see the plane going up in that fashion there. But if you watch the shadow on the ground, you actually see it going just the horizontal position, and that's what we're measuring for this right here. How fast is it going using the trigonometry involved? Well, this is adjacent, and we know the hypotenuse, so that means the cosine is what we're going to use here, SOHCAHTOA. Okay, so that means the cosine of 20 degrees is equal to the adjacent, which is our vertical, or rather our horizontal velocity, over the hypotenuse, which are 255 kilometers per hour. And so what's going to happen then is that we simply multiply by the denominator to get the VH by itself, and that gives us 240 kilometers per hour. All right, now we take care of the blue one, the vertical velocity. And this is where the situation here, where you're standing in this direction and the plane's coming right at you, but it lifts up at that 20-degree angle, but all you see is how fast it's rising here. So that is the perspective you're going to have for this right here. So we're going to find this value here using the opposite over the hypotenuse, which is the sine. And so the equation we're going to use here is that the sine of 20 degrees is equal to the opposite, which we said is the vertical velocity, over the hypotenuse, which we have established is 255 kilometers per hour. And like what we did with the cosine, we simply multiply by the denominator, 255 kilometers per hour, multiply that together, and we actually see it go up only at a little bit more than 87 kilometers per hour. So those are the components you're looking at. So every time that we look at an oblique vector that is not perpendicular to the ground, which hopefully, unless you're in a helicopter, is not going to happen, because that means it's crashing, and we don't want people dying just for the sake of math. Anyway, so that means then that we have established the two horizontal, vertical, the two components for that scenario. And so the problems in the book that you're going to use for that exemplifies that, problems 2B, 4, 8, and 12 on pages 96 and 97. Good luck.